what background needs to do and how to do it. I just want to know how to tell it when to do it. And that means the disk has to tell us that there is background work to do, right? There's a couple different ways that can happen. In the paper, we talk about profiling data and ways to understand what the disk is after. My mental picture of this is the host periodically schedules background work. You could think of it as being as simple as an API such as, please do some background work now, or do background work for K tracks. K is nice because then it can pick a bunch of tracks that are near each other and do them all together. And the implication of that call is that I'm not going to send you any latency sensitive reads in the near future. So this is a good time to do background work. So we won't curtail latency, and even better would be, oh, by the way, I changed my mind, it'd be nice to cancel the background work, but even if you couldn't cancel the background work, it would still be better to have an API that says this is a good time. But of course, the host might forget to do that, and so one answer would be, there's a timer, and if the timer goes off, the disk can do whatever it wants. So if the disk says, oh, I need to do background work, you said you'd call me and you didn't, I'm going to do it now, right? And the host shouldn't let this happen, right? If the host lets this happen, it deserves whatever tail latency it gets, right? It didn't meet its end of the contract. So that's a flavor of the kind of timing control I'm thinking about here. Again, leaving the details of what to do to the disk and when to do to the host. Another complication here that's related to tail latency is we actually label, again, per IO, all of our reads. So we're labeling at all layers of the system, basically. This is a low latency read, this is a throughput read, which you could think of as it's a performance-oriented read, but it's not latency sensitive. That's most commonly used in batch work. And then best effort is our own kind of background work, like background scanning or data repair or movement, things that are not time critical and where we would not want them to interfere with live services or actual performance work. So we have these three classes. We use them now with the disks we have, and they make they're very helpful in the higher levels of the system. Of course, they're not that helpful for the disk. I'll talk about what we do to fix that. You'll figure it out probably, but it's kind of cute. But let's get back to what the labeling is. So in addition to having the labels, to get them to work, you actually have to have admission control as well. Otherwise, every read wants to be a low latency read. And they all have to be faster than average. That doesn't work, so we have quotas for the first two categories so that we can limit how many such reads can come into the system in general. And by the way, this is something that infrastructure has to put on the application developers within Google. Because again, for every application writer, they would say their application deserves all low latency reads. And we have to say, no, you get this many. You don't get that many, right? So you do have to have admission control, and that means you're going to have to do some throttling, which we'll talk about in a minute. And then we track all these things in all of our own systems and monitoring. So we know, for example, separately our latency for low latency reads versus our latency for throughput reads versus our latency for best effort reads. And likewise for writes. And for bandwidth per second and all kinds of other obvious metrics. So that's the labeling, and it really does help, but what do we do for the disk? Well, since the disk doesn't know about labels, we actually, if we really care, we have to give the disk one IO at a time. That's the most correct solution. That has some problems. If I give you one IO at a time, then if a new low latency read arrives, I can put it at the front of my queue and it'll be the next thing I give you. If I give you all the IOs I know about and a low latency read arrives, all I can do is put it at the end of your queue, you the disk. Right? That doesn't work. So in fact, we don't give the disk a lot of IOs to choose from, which means that we're not taking advantage of elevator scheduling. Right? So we're forfeiting something to get control over latency here. Now, there's a partial solution called native command queuing. It's not really intended for per IO labeling, but it could be. There are versions of it that do. And in this model, what we would like is that the host manages the quotas. The host does the throttling to make sure not too many low latency or throughput IOs come through. But the disk needs to do the reordering. So I'd like to actually give a group of IOs to the disk, label them with these labels, and have it decide, based on its knowledge of the head and the tracks and what else is going on, which IOs to do in what order. That's something it can do better than we can do, but it has to know what our labels are and what they mean. So in particular, we need a way to talk about the labels. We need a way to talk about the latency targets. Because in some sense, what's going on inside the disk ought to be a real-time scheduler that knows about deadlines. It says, oh, I'm running out of time to do this low latency read. I better go do it now. Right? And the paper covers about other things, like maybe I want to put new operations at the front of the disk queue instead of the back, or maybe I want to cancel things that I've already given to the disk to do the cancel of requests. That would be very useful. There's quite a large variety, and this I actually think is something that would be a very good place to explore in academia, because it's wide open what this balance should be. Right? But it's definitely not the current solution where we hand this one thing at a time, or the other current solution where we hand them a bunch of stuff, but now we forfeited control over latency to whatever the disk scheduler chooses to do. Now, those are all tail latency things. Getting back to the collection view, there's another factor that's interesting, worth some discussion, which is how we think about disk drives in aggregate. Well, the first point is we always mix a variety of drives, even within one data center, and that's because we buy them at different times. So at any given time, we'll buy basically the best disk we can. For best is a very hard thing to define. But the point is it changes every year. And so naturally, you have disks that last many years. You end up with a mix of disks in your fleet with fairly different capabilities. So the way we address this is we have overall goals for the total IOs and total gigabytes that we want to have. And then when we buy new disks, we essentially are looking for disks that get us closer to our marginal targets, meaning that the marginal addition of those disks, IOPS and gigabytes, bring us closer to the balance we want, right? So it's very different than how you buy a disk for a server, where you think about that server in isolation. We're actually thinking about the fleet-wide metrics. So here's a graph that we use to think about this. It's a little bit complicated, so I'm going to walk through it. So the axes first. Vertical axis gigabytes per dollar, which is dollar here means total cost of ownership, but how many gigabytes do I get for every dollar I spend on this particular disk? Again, filtered carefully to include its maintenance and things like that. The x-axis is IOs per gigabyte. Right, so this means if the disk gets bigger and doesn't get more IOs, it gets worse by this metric. So in fact, most new disks are worse on this metric than their predecessor, because they get bigger more than they get faster, right? That's what makes this thing a little bit complicated. So it is structured that up and to the right is better, right? So in this case, F dominates E. If you had choice of these two drives, you should always buy F. It has more capacity and more IOPS. You would never buy E. Right, that's the easy case. The problem is all the things that you can muck with on a disk tend to be top left to bottom right, right? Meaning like platter size, if you make it bigger, you do better on the y-axis, but you do worse. Sorry, you do, yes, you do. You can't get to the upper right, basically, just changing the platter size, right? If you make the platter bigger, you get more gigabytes, but it costs you more. Sorry, I mean, you get less IOPS per gigabyte. If you make the platter smaller, you do better on IOs, but now each gigabyte costs more. And it's the same with RPM. It's actually the same with a lot of other metrics. And so it's hard to get to the upper right. If we had disks in the upper right, we would buy them, right? They don't exist. In fact, we're not the first group to ask for more IOs, right? People would asking for more IO operations per second for disks for a long, long time, right? So what we end up seeing is lines that look like this, where we're choosing between C and D as our mix. And again, these are two specific drives. These, by the way, are not real drives. These are fake abstract drives. That's not some vendor's drive there. It's a totally made up point. But the way we think about it is accurate. So one thing that's useful about this graph is, suppose we had a target IOPS per gigabyte, which is our fleet-wide goal, we can get that, it turns out, by a linear mix of C and D. So you just take your target and you figure out where it crosses that line, and that's the ratio of disks you buy between C and D. And they will give you the optimal mix, given those two disks, of gigabytes and IOPS that you can get. And when you extend that to what we actually do broadly is you take all the disks you can buy, you compute the convex hull, and the top of the convex hull, which are the red lines, is the disks you should buy depending on how many IOPS per gigawatt you want. Right. So that's how we actually think about disks. And when you think about disks this way, it actually makes a lot of sense because, again, the individual disk doesn't matter. Only the fleet metrics matter. By the way, that's assuming you can actually use your IOPS and your gigabytes no matter where they are, which is not that easy. But we do that generally. I can talk more about that later if you want. And again, you tend to see these slopes. Again, the line never slopes up and to the right. It always slopes down and to the right, because if it didn't, we would just buy the dominant disk. So we're always looking at this kind of trade-off to try and figure out how to do a mix. And likewise, if we're trying to move the fleet average, we can get the marginal IOPS per gigabyte that we want for the new disks using the same graph, and that's what we buy, right, to move the fleet average. So there's a lot of consequences of this. I'll just cover a few of them. One of them is we don't care about how much capacity there is per disk very precisely, right? We always buy 6 terabyte disks or 8 terabyte disks, whatever they are. It changes obviously every year. It's actually hard to make a disk that's exactly 6 terabytes. The way you do that is you produce a disk that's bigger and you don't use some of the sectors, right? Well, those sectors are wasted. And by the way, if you got a disk that was 5.9, do you not sell it? Do you remanufacture it? We would take it, actually. We'd be happy with a 5.9 gigabyte disk, assuming it's otherwise perfectly fine disk. So the way to think about it is we don't care about how big it is precisely, but we do care how many sectors are good. You might as well give us all of them. No reason to hold them back. That means that the disk will get smaller over time as sectors fail. That's okay. Doesn't matter. So we don't need it to be constant. That's another interesting thing. It's okay to mark sectors bad. It's even okay to remap them on the same track. We'd rather you not remap them to other tracks, which just sometimes do, because that ruins the tail latency. We do a sequential read, and in the middle of the sequential read is a jump to another track to get a remap sector. Right? That's not so good. We would rather throw that track out, or those sectors out, than actually have that remap jump. Most of the time, to be clear, the sectors are remapped to the same track, and that works fine. But there's only so many extra sectors per track, and after that, they have to be mapped somewhere else. More interestingly, we'd actually be perfectly fine if we could use a disk after one of the heads or platter fails. Right? So we lose one fraction of the disk. We probably have to reformat because the LBAs are spread all over the disk. But that's okay. We could just reinitialize the disk and use the capacity and IOPS of that now smaller disk. And it would fit into what we do, and it would actually cost less over time because now we're getting longer lifetime out of that disk. So it's not that we want flaky disks, it's that if flaky disks cost less, they might be a good thing to buy. Right? It's the trade-off that's interesting. All this time I haven't mentioned SSDs. And the short answer is we don't really use them as the core of our storage today. We do use them. We use them for caching in higher level systems. It's very good for absorbing various reads and writes high in the stack. It's an excellent place for work because those are more expensive. It's also quite good for certain high performance workloads. We do have some. But in general, the cost per gigabyte is too high. I think people agree with that. I think the part that's more surprising is it's relatively close, the improvement rate of SSDs and disks. Close enough that even though SSDs are improving at a great rate, they're not catching up at a great rate because the hard disks continue to evolve themselves. It's very hard to know the actual rates for both of those. We have internal data we look at all the time. There's several things on the line, online from different vendors. And by the way, you'll get different views from SSD vendors than you will from hard disk vendors. So I chose not to quote either one of them. But what we're seeing is, especially if you include program erase cycles, the SSD growth rate is not that different from the hard disk growth rate. Right? If we had a giant SSD, but we couldn't program erase it that many times, which is pretty typical, it actually isn't usable in our fleet. Right? And by the way, going all the way back to InksMe was the same way. The disks in these services are much busier than disks in general. Right? Because you're essentially concentrating a whole bunch of activity to the minimum number of disks that can handle that activity. And so your utilization is high and your IOPS is very high. In fact, we used to beat the crap out of our disks, frankly, doing search engine stuff on those early disks. They were not ready for it the way they are today, frankly. They're much better disks now. So the program erase cycles actually are a limiting factor at SSDs at the moment. I do think this is going to change. I just don't think it's as quick as people think it is. So I'm saying 5 to 10 years we'll still be using disks. And part of that is, again, is the exponential growth in demand. So if we had a fixed amount of storage, I think SSDs might make sense sooner. But the growth is also exponential in demand, so it's going to be a long time. So in general, we left SSDs out of the white paper and out of this talk, and again, it's not that they're unimportant, they're super important, but for actually solving large-scale storage, we're not depending on them much. Finally, a little shift. It's worth knowing that the modern disk dimensions, the 3.5-inch disk, takes its power and its dimensions from the PC floppy disk. And I mention this because it might not be optimal.